This is chemistry. The unit is solutions. So I'd like to begin the unit by asking you which of these are solutions. So first you have the atmosphere, so the air that you're breathing in. Next you have a can of Dr. Pepper, so when you're drinking that Dr. Pepper, are you drinking a solution? Coffee, whether it's black coffee, coffee with cream and sugar, a frappuccino, a latte, are you drinking a solution when you're drinking your coffee? What about the gasoline that goes into your car, whether it's 87, 89, 93. Here in Illinois, we have a 10% ethanol label. So is the gas that goes into your car a solution? Cough syrup. So if you've ever taken cough syrup, what do you know about it? Does that make it a solution? And then finally, brass. So it's not really the instrument, it's what makes up the instrument. So is that brass a solution? So what do you think? Which of these are solutions? Are any of them solutions? Or are all of them solutions? So the answer is all of them. So why am I pointing out these different substances here, right? So brass, if you remember, is copper and zinc. So that's two metals, right, put together to make that shiny brass. You have cough syrup, right, which is the medication, some flavoring, some sugar, some water. So you have most likely liquid and solid in there, right? Gasoline with that 10% ethanol and the different grades, that's going to be liquid and liquid. The coffee that you're drinking is usually liquid and liquid. You could have like some chips in there for a mocha frappuccino. You could also have some sugar dissolved in there, which is another solid. So it's usually liquid and liquid or liquid and solid. Your soda is usually your high fructose corn syrup. That's a liquid with some water, with some flavors. And then don't forget you have that carbon dioxide also mixed in there. And then the air that you breathe is nitrogen, oxygen, and quite a few other gases, right? So yes, all of these are solutions. What exactly does that mean? Well, a solution is defined as any substance, solid, liquid, or gas, which is what I was just trying to go over, that is evenly distributed throughout another substance. And another word for solution that we did learn in semester 1 was homogeneous mixture. And that's when we talked about brass. Now there are two parts to every solution. You have the solvent, which is the substance doing the dissolving, and the solute, which is the substance being dissolved. And what exactly does dissolve mean? This is a process by which a solvent separates the components of a solution. So be careful, this is not a chemical reaction. Okay, components are being separated. And this process of dissolving is also called solvation. And this is a good image for you to look at. So the NaCl here is the green and the bluish purplish molecules connected. So this is NaCl. And then in the background you have the water, which is the red and the turquoise. So as this NaCl remains in the water long enough, you can see that the Cl and the Na are starting to separate. And in that last picture, they're completely separated. So this is dissolving. It is a separation of the components. Now, an important kind of solution is called an aqueous solution, and an aqueous solution is a solution where water is the solvent. So aqueous kind of sounds like aqua, which is a reference to water. Now, the basic rule in chemistry is like dissolves like. So we talked about dissolving. What is this idea of likeness? So here's what it means. So if like dissolves like, that means that the components are miscible. So a polar solvent will dissolve a polar solute. A nonpolar solvent will dissolve a nonpolar solute. So they are miscible. The solute and the solvent are miscible. Now, if they're immiscible, polar solvents do not dissolve nonpolar solutes. Nonpolar solvents do not dissolve polar solutes. So if a solvent is polar, but the solute is nonpolar, they won't dissolve, and then vice versa. So what does this mean? We did learn polarity, so let's just refresh this, right? So if I asked you water and ammonia is a common name, so I gave you the formula, it's NH3. Are they miscible? So how would you figure this out? So the way to figure it out is what we learned over several chapters. So the first thing you'd have to do is draw the Lewis structure for each one. So you have water on the left and ammonia on the right. The next thing I did was put in my dipoles, which are those arrows with a little bar at the end here. So the direction of the dipole was towards the more electronegative element. So oxygen is more electronegative than hydrogen. You can actually look up those numbers. You had a chart for that. Same thing here, nitrogen, more electronegative than hydrogen. So all the arrows point to nitrogen, all the arrows point to oxygen. So by looking at the dipole and the fact that both of these are just surrounded by hydrogens, you would think that they're both nonpolar because they look symmetrical. But that's not the case. Both center atoms have pairs of electrons, and that throws off the symmetry and makes them both polar. So water is polar, NH3 is polar. So are they miscible? The answer is yes, they will dissolve in each other. Like dissolves like, because they're both polar. What about water and carbon tetrachloride, which is CCl4? Are these two miscible? So here we go. We already discussed water. There's the Lewis structure, there's the dipoles, but it is polar because the center oxygen has those extra pairs of electrons. But now take a look at CCl4. So you have carbon with 4 bonds, and each bond is connected to a chlorine, right? The dipoles are also facing the same direction. So this is quite symmetrical, which makes it quite non-polar. So are they miscible? Polar water, nonpolar carbon tetrachloride? The answer is no. So they will not dissolve in each other. So what does this all mean? Well, let's look at this question. For example, is it possible for a solvent like water to dissolve an indefinite amount of a solute, such as salt? So can you just, let's say you have a cup of water, can you just keep adding salt to that indefinitely? And that cup of water will continue to dissolve it. The answer is no, there's limits, okay? Now, how can you tell if a limit has been reached? You can tell by what's known as solubility, which is a measure of the amount of solute that a solvent can dissolve. Okay, now qualitatively, which means by description, right? We're going to start with qualitative descriptions here. So a solution can be described in 3 ways based on this idea of solubility. You can have an unsaturated solution. So this is a solution that has not reached the maximum amount of solute that can be dissolved by the solvent. And a good example is making Kool-Aid from that little packet. So if you use that little packet and add some water to it, depending on how much you're adding, if you follow the directions and whether or not you want, a sweeter or a less sweeter Kool-Aid, that is unsaturated. The fact that you can keep adding more to that water to make it taste better and you don't get anything settling at the bottom, that means that that water is unsaturated. It can take more of what you want to put into it. So the way to tell if it's saturated is the fact that it would settle out, which is the next concept. A saturated solution is a solution that has reached the maximum amount of solute that can be dissolved by the solvent. So just take a look at my image there of the chocolate milk. While that might be tasty, it's actually made incorrectly. So that milk can't hold all of the chocolate that was added. So if you look at the bottom of the glass, you can see the chocolate has settled out because this is a saturated solution. The milk can hold no more chocolate. Now, a supersaturated solution is a solution that can actually dissolve more than the maximum amount of solute that can be dissolved by the solvent. And you get a pretty cool outcome. You can actually get crystals. So a lot of chemicals will actually make crystals, which is what you see on the left. But then there's this concept of rock candy. So rock candy is very, very basic. It looks pretty, but it really is just sugar and water. And how you get rock candy is, for example, to take 1 cup of water and heat it up, but add 2 cups of sugar to it. Now, 1 cup of water should really only hold 1 cup of sugar. But if you heat it, right, and continue to stir it, you can get 2 cups of water, 2 cups of sugar dissolving in that 1 cup of water. And then if you let it settle out, you will get crystals. So it takes a little while to actually do this, but it's a very pretty result. But that is super saturated. So it's more solute than that solvent was supposed to hold. All right, now what affects the solubility of a solute in a liquid solvent? First of all, the temperature of the solute and or solvent. So temperature, remember, is a measure of kinetic energy. It's not a measure if something is hot or cold. So if you increase the temperature, you are increasing the kinetic energy. So the higher the kinetic energy, the higher the ability to dissolve that solute. Mixing. If you mix a solution, you increase the kinetic energy. You are moving that solution, right? So a higher kinetic energy means a higher ability to dissolve that solute. And then increasing the surface area of the solute. So if you crush a solid solute, you increase the surface area of that solute. And what happens then is that higher surface area of the solute equals a higher area that the solvent can attack the solute. So if you just think of adding sugar cubes to coffee or tea versus that granulated sugar to coffee or tea, which will dissolve faster? It's going to be the granulated sugar because it has a higher surface area that the solvent can attack. So increased surface area that the solvent can attack the solute equals increased dissolving. Now, qualitatively, you can determine exactly how much solute can dissolve in a specific amount of solute. So if you take a look at this chart, here are different substances. These are basically salts. You probably recognize NaCl, and you have different temperatures. So as the temperature is increased, you can see these numbers in these boxes indicate how much of this substance can dissolve in a certain amount of water at these different temperatures. So if you look at Ki, for example, you got a lot that can be dissolved here versus NaHCl3, where there's not too much. Okay, but this data can also be graphed, and it's a little bit easier to look at as a graph, and it's known as a solubility curve. All right, so this is where we are going to finish up here. So this is a solubility curve. So what is it that you're actually looking at? Well, let's just look at the curve of the graph itself. So on this x-axis, you have temperature in degrees Celsius. On the y-axis, you have grams of solute in each of these chemicals in here. These are salts, that's your solute, that are dissolved or per 100 grams of water. So each one of these has been dissolved in 100 grams of water. And as the temperature is heated, you can see how much is being dissolved. Okay, so I'm going to show you now how to actually read this. So what I have done is for each of my 5 questions, I focused on potassium iodide, which is the Ki here, all the way up in this corner, so that it's pretty easy for you to follow me. I didn't want to pick one of the lines here because it might get confusing just from watching this video. So we're going to focus on Ki up in this top corner, and let's answer these questions now to help you understand this. So my first question is how many grams of potassium iodide can dissolve in 100 grams of water at 10 degrees Celsius? So I'm going to put my pen here. Okay, so what does this mean? So this is Ki. 100 grams of 100 grams of water just tells you how much water it's being dissolved in. But you need to focus now on this 10 degrees Celsius. So if you look at 10 degrees Celsius and go all the way up to the line Ki, so where it exactly reaches it, okay? What is that amount of Ki? So you have to look to the left, and you kind of have to estimate here. So for me, that's looking like 138 grams of Ki. So that is how much will dissolve in 100 grams of water at 10 degrees Celsius. So that's how you read it. Now look at my next question. So it says, how many grams of Ki can dissolve in 300 grams at 10 degrees Celsius? Where are you going to get 300 grams? Well, it's pretty straightforward. If this is 100 grams, right, if 138 grams dissolves in 100 grams of water, well, if you triple the amount of water, you'll triple the amount of Ki that can be dissolved. So just take the 138 and times it by 3. And I got 414 grams. All right, but the neat thing now is to get you to understand the terms saturated, unsaturated, and supersaturated as you're reading this graph. All right, so let me get another color up here. I'll get green. Okay, so here we go. So I have 145 grams of potassium iodide Ki that dissolves in 100 grams of water. So we're leaving this as 100 grams at 20 degrees Celsius. So let's just find this first. Here's 20 degrees, and if I go up to 145, that is this point right there on the line. So the question is that saturated, unsaturated, or supersaturated? Now, if that point is exactly on the line, we call that saturated. Okay, let's get another one here. So what if I have 140 grams, still in 100 grams of water, still at 20 degrees? So let's go to 20 degrees and mark 140, which is there. So this is now under that line. It has not reached the line for Ki. So that makes it unsaturated because it hasn't reached the point of saturation, which would have been 145 grams. And then last one, what if I had 150 grams of potassium iodide or Ki, still in 100 grams of water, still at 20 degrees? So let's go 20 degrees and 150. So now that's way above the line. So we call that super saturated. So on the line, saturated, under it, unsaturated, and above it, super saturated. And that's how you read a solubility curve.